Great.
Good. Okay, so what's the plan? So it's this. So I'm going to start off by presenting you Reichenbach's idea of a constructive axiomatization of a physical theory. I'm then going to introduce you to two particular types of structure. They'll be familiar to lots of you already, which are going to form the basis of lots of different constructive axiomatic approaches to general relativity. And I'm going to go back to the history a little bit and see Reichenbach and Weyl debating what a good constructive axiomatization of general relativity would look like. And then we're going to see the kind of completion of the Weylian project, or what people often regard as being the completion of the Weylian project, with a very famous 1972 paper by Ehlers, Pirani, and Shield. I'm going to point you to certain aspects of this axiomatization, which one might regard as being suspect. And we'll see what you think of those. I think there are certain places where there's room to push on what EPS are doing. I'm then going to talk about some various developments of the Ehlers-Pirani-Shield constructive axiomatization, which have followed since the early 70s when they did their work. This is the place where I think there's a bunch of physics literature which we as philosophers of physics should engage with more. And then I'm going to make some closing foundational remarks. If any of you have any questions throughout, just shout or stick your hand up. Great. Okay, so here's a kind of one-page slide of history. So we all know that after a pretty much decade-long struggle, Einstein completed his general theory of relativity in 1915. And around that time began a golden age of the interaction between physicists and philosophers and mathematicians. So Einstein was in heavy correspondence with Reichenbach. We had people like Cassirer on the scene. There was lots of very, very interesting interaction around that time. And one of the things which came up, or people were interested around that time, was what it is to axiomatize a physical theory. And people like Reichenbach saw general relativity as being a good testing ground for different ways of approaching the axiomatization of a physical theory. It was both mathematically precise, but also had what people thought to be fairly straightforward empirical correlates with its mathematical structures. So a good testing ground for foundational questions regarding axiomatizations. So in these discussions, for our purposes today, the two main protagonists need no real introduction. And on the one hand, we have Hans Reichenbach, here he is, and on the other, we have Hermann Weyl. And the main piece of literature which triggered the field of constructive axiomatics was this book by Reichenbach, which came out in 1924 in its German edition, Axiomatization of the Theory of Relativity. Here we have the English 1969 translation by Maria Reichenbach. And in this book, Reichenbach lays out what he calls a distinction between deductive versus constructive axiomatizations of theories. So here's how he presents a deductive axiomatization of a physical theory. We begin with some elementary axioms, perhaps selected on the grounds of mathematical simplicity. You want to construct your theory from very, very mathematically simple axioms. You build up your theory from those axioms, and only then do you correlate the various objects in your theory with various aspects of the empirical world. That methodology is kind of different to the methodology underlying what Reichenbach calls a constructive axiomatization. Here, the idea is that you begin with some elementary axioms which are not selected for their mathematical simplicity, but rather which are from the outset correlated with elements of the empirical world. From there, you build up your theory from those axioms. And the thought is that in that way, the entire theory can be known to stand on firm empirical foundations. We'll see more about what this means, and it will become clearer when we look at particular examples. But here's a relatively famous quote from Reichenbach in that book where he's distinguishing the two approaches. He writes, "It is possible to start with the observable facts and to end with the abstract conceptualization. A certain loss in formal elegance will be balanced by logical clarity. The empirical character of the axioms is immediately evident, and it is easy to see what consequences follow from their respective confirmations and disconfirmations. Such a constructive axiomatization is more in line with physics than a deductive one, because it serves to carry out the primary aim of physics, the description of the physical world. So just to repeat, in a constructive axiomatization, you want your axioms to have immediate empirical correlates, and then from there build up your theory, rather than having axioms which are selected for some other reasons. Good. So we'll have a quick interlude on different kinds of structure, the kinds of structures which are going to be particularly important in constructive axiomatizations of general relativity. And then I'll return to the history, the debates between Weyl and Reichenbach. For our purposes, the two structures which are going to be of particular importance are conformal structure. So two Lorentzian metrics are conformally equivalent just in case there exists a function such that one is the kind of scaling by that function of the other one. And projective structure, so two connections are projectively equivalent just in case there exists a one form such that the connection coefficients are related by this. This means that they agree on the trajectories of free particles up to reparameterization. These terms can be associated with reparameterization. And now the very rough idea, which is going to underlie a lot of constructive axiomatizations, is this. We're going to look to the world lines of massless particles, i.e. the trajectories of light rays, and eventually we're going to want to associate those or build up from those conformal structure. And then we're going to look to the world lines of free massive bodies, and we're going to eventually want to associate those with projective structure. And if I can extract from these things, which the claim is I can immediately empirically observe the trajectories of these different kinds of particles, then the thought is I have enough information to be able to reconstruct the metric of general relativity. This goes back to a theorem from Weyl from the early 20th century. Here's how Malamant puts it in his book. Assume I have two metrics such that one is some rescaling of the other one. Further, assume that these two metrics agree as to which smooth time-like curves can be reparameterized so as to be geodesics. Then this omega is a constant. So if I have my conformal structure and I have my projective structure, then I have the same metric up to a constant factor. So the thought is if I can get my projective structure from my massive particles, I can get my conformal structure from my massless particles, then I can reconstruct from that the metric field of general relativity. The idea thereby is that I've put general relativity onto solid empirical foundations by building it up from these things which are directly observable. Obviously, I'm not endorsing that. There's a lot to question, but that's the idea. Okay, so let's quickly go back to some of the history. This is a really, really fascinating exchange, and I learned much of what I know about this exchange from a very, very nice 2005 paper by Robert Reichenbach, which I would recommend to you all. So that's in the bibliography of these slides. So let's start off with Reichenbach on axiomatizing special relativity. His book really divides into two parts. The first part is just about the axiomatization of special relativity, and then he moves on to the axiomatization of general relativity. So in the Axiomatik, Reichenbach maintained that the structure of special relativity can be built up from the paths of light rays alone. Now, Weyl did not like this at all. He pointed out to Reichenbach that you also need the paths of force-free massive bodies, pretty much for the reasons that I went through in the previous section, which are going to be associated with projective structure. Now, as Reichenbach documents in his very nice paper, Reichenbach repeatedly ignored these points from Weyl, somewhat winding the latter up. So I'd recommend this story not only for the interesting physics involved, but also because it's a fascinating tale of philosophical beef. Here's how Reichenbach summarizes this situation. He writes, to sum up, we find in Reichenbach's Axiomatik not only the insistence that a problem can be solved that Weyl had long ago argued cannot be solved, but also not even a mention that it was Weyl who had alerted him to the problem in the first place. So Reichenbach doesn't come off too well in Reichenbach's telling of this story. Moving on to general relativity, Reichenbach actually takes a very different approach. So in this case, Reichenbach sought to use idealized rods and clocks in local neighborhoods in order to reconstruct the metric field. This didn't meet with a good reaction. for a bunch of reasons. So you might protest that first, his use of local neighborhoods is not very well defined in this book. In addition, it's an odd switch. Reichenbach moves from thinking about massive and massless particles, very simple empirical things, to complex bodies, such as rods and clocks. And a lot of people objected that you can't presuppose these complex bodies in a true constructive axiomatization of a physical theory. So Weyl was one of those people. He thought that a better way to go would be to use this proof. So I've already told you that he showed that projective and conformal structure fix a Lorentzian metric up to a constant. The idea then would be that you can use this observation as the basis for a constructive axiomatization. So if you associate the conformal structure with the paths of massless bodies and projective structure with the paths of force-free massive bodies, then that's going to afford the means to identify the metric of general relativity in terms of these structures. Now, after that, not so much was done for about half a century, but the project was picked up by Ehlers, Pirani, and Shield in the early 70s. And they really brought the Weylian idea of a constructive axiomatization to full fruition, to maturity. So here's the start of their paper. I would recommend it to everyone. Hard to think of a more foundationally significant paper in the second half of the 20th century. So in this paper, EPS lament doing a constructive axiomatization on the basis of rods and clocks. In that sense, they are voicing the concerns about Reichenbach's approach to general relativity, which many of us, well, which we've already seen and which many had already raised. So rather, they take Weyl's theorems from the 20s as their starting point. But they go beyond these in a number of regards. So to highlight just three, first of all, they also seek to build up the differential structure of the manifold from elementary assumptions, from constructive axioms. Second, they're concerned with how one tracks massive and massless particles in order to recover projective and conformal structure. You know, if you're really doing an axiomatization, which is meant to begin from empirical foundations, it's all well and good to say, if I had the trajectories of massive and massless bodies, I could construct a metric field. But you also need to be able to like figure out what the trajectories of massive and massless bodies are. So there's a bit more to say there. How do I know what the trajectories of these bodies are as an agent at a particular spatiotemporal location in the world? So they're concerned with this second question as well. And I think it's also important to stress this third point. So I think many people, when they first look at EPS and they look at Weyl, it's somewhat unclear what the difference between these two is. I think the best or a good way to understand the difference is this. So Weyl demonstrated a uniqueness claim. Given a piece of metric structure, it's fixed uniquely by some projective and some conformal structure. But EPS kind of start with the second. So they say an existence claim. Given any piece of projective structure and any piece of conformal structure and certain additional minor input assumptions, which we'll go into, they claim that these will allow you to construct a metric field. So in this sense, they're really, you know, doing what you would really want from a constructive axiomatization. They're starting off with these structures and they're building up a metric structure. Good. At the start of their paper, there's this very, very nice diagram in which they summarize their methodology. So I hope everyone can see this. It may be a little small. So they start off with a manifold and differentiable structure. Then they're going to want to build up projective structure, and they do this from the world lines of freely falling particles. Then they're going to want to build up conformal structure, and they do this from the trajectories of light rays. They impose certain axioms about the trajectories of freely falling massive bodies to get this. They impose certain axioms about the trajectories of light rays to get this. Once they've got projective and conformal structure, they then input an assumption, which is the compatibility assumption, which is that the trajectories of the freely falling massive particles fill the light cones, which are given by the conformal structure. This is what they call the compatibility assumption. This allows them to get a Weyl geometry. In general, it's going to manifest the second clock effect, which, as many of us know, is what led to Weyl's geometry being regarded as being empirically inadequate in the 20s. They impose an integrability condition, which means that there's no second clock effect. This is the thing which led to Weyl geometries being regarded as being empirically inadequate. Basically, if I start off with two clocks and transport them along different paths and bring them together again, it might be that they still read the same time when they get brought back together. So there need not necessarily be any kind of twins paradox effect, but it might be the case that one of them is now ticking at a different rate to the other one. If that's the case, then we have the second clock effect. They impose a condition which rules out the second clock effect. And rightly, many people have questioned where this condition which they impose here comes from. We're going to come back to that. But eventually they get up to some Riemannian structure via this kind of, to their Riemannian space-time structure via this procedure. The diagram is slightly misleading in the sense that 90% of their paper is dealing with the stuff right up here. Constructing these things takes a lot of work, but actually this takes not that much work.
Sorry, James, quick question. Could you develop a little bit on the third section?
Is that this one or this one?
Well, the one below, yeah.
This one?
Yeah.
So they get a Weyl geometry. One way to understand a Weyl geometry is as having non-metricity. And they want to get from that to the more restricted Riemannian context. And they do that by imposing certain extra input assumptions to move us from the general Weyl geometry context, then to the integrable Weyl geometry context, where you don't have a second clock effect, and then eventually to a Riemannian context.
What's the diagram on the right that says P1, P2 equidistant, Q1, Q2 not equidistant?
That is actually a good question. I generally just look at this one. I'm afraid I don't immediately know.
And the one on the left?
So this is talking about parallel transport of vector length along a non-null curve. So you can understand the second clock effect as arising when the length of a vector isn't the same when you bring it back together again, when you parallel transport it along two different curves. So I assume it's related to that.
Okay. Thanks.
We can maybe, we can maybe figure, Maybe let's come back to it. I mean, hopefully the rough idea is clear.
So can you just distinguish the first and second clock effect a little bit? I'm not sure everyone knows that.
So as far as I understand, the first clock effect is the twins paradox, where when you transport along two different paths, it might be that the length of those curves is different. So just a twins paradox type effect. A second clock effect would be where, so you start off with two identical clocks. I'll transport one along one path, one along a different path. They might have elapsed different times when I bring them back together again. That would be the twins paradox, the first clock effect. The second clock effect is where it might be the case that if I do this transportation, the clocks still read the same time when I bring them back together again, but the rates of the clocks are different. So one is ticking at a different rate to this one when I bring them back together again. That would be a second clock effect. And that effect was what led people to get off the train of Weyl's approach to the unification of GR and electromagnetism in the 20s.
That was very clarificatory. Thank you.
Cool. But we have Neil in the audience who's just written a paper about this, so I'm sure he'd be able to say lots of other useful stuff. Let me say a bit about EPS, and then, I would like to figure out exactly what's going on in these diagrams, I agree. But yeah, cool. So I'll sketch to you the kind of idea of their methodology. So they're going to build up differential, projective, and conformal structure from three sets of axioms: the D axioms, the P axioms, and the L axioms, L for light. Sometimes these axioms are used in seemingly very non-trivial geometrical constructions. I should say that one of the things which I'm trying to do right now, which surprisingly to my knowledge still hasn't been done, at least in the level of detail I would like to see, is really go through and clearly and explicitly present exactly what's going on in the EPS axioms. At the start of their paper, they say, yes, everything here isn't completely rigorous, but it seems morally right. They have something to that effect. But we, by which I mean myself and my collaborator, Niels Linnemann, are kind of at the moment trying to go through and render everything completely explicit here. Perhaps it is the case that for people as smart as Ehlers, Pirani, and Shield, it's obvious what they get out of these axioms indeed follows, but I'm not as smart as them, so I would like to see it a bit more explicitly. So this is all to say that the axioms are often used in subsequent geometrical constructions, which require some reflection in order to see whether what's claimed to follow indeed does follow. Other times, it looks like the axioms rule out by fiat certain geometries. So what I want to do in the next few slides is to point out places where, to my mind, that happens, where by certain kinds of moves that they make, they're implicitly ruling out certain geometries. If that's true, then the approach doesn't deliver us what we wanted. Maybe it delivers something more general than a Riemannian geometry. So let me flag to you 3 places in the approach where this seems to happen. The first issue comes up in the first light axiom of their paper. So this is one of the more complicated axioms. It says any event E has a neighborhood V such that each event P in V can be connected within V to a particle, by which they mean some time-like trajectory, through E, to a particle by at most 2 light rays. So we see that P here is connected to this particle trajectory by 2 light rays here. But if P were here, it would be connected by just 1 light ray, because this point would be outside of the region V. Moreover, given such a neighborhood in a particle P through E, there is another neighborhood U within V, such that any P in U can in fact be connected with P within V by precisely 2 light rays, and we've got that here. And these intersect P in 2 distinct events, E1 and E2, if P is not on P, little p is not on big P. Now, if they introduce a coordinate along P, which they call T, with T, the coordinate assigned to E being 0, they then define this function G, which maps P to the coordinate which is assigned to E1 times the coordinate which is assigned to E2, as illustrated by this diagram. So essentially, they've got this kind of, kind of like what I was saying, it's quite a complicated geometrical construction, but what they've ended up doing is they've assigned points off this particle trajectory, big P. They've assigned each of these points, little p, some number is given by this function, which is the product of the coordinate assigned to E1 and the coordinate assigned to E2. And then they go on to do various things with that. The point that I want to make, which has been picked up recently by Lamezel and Perlich, who are physicists in Bremen, is that it's quite unclear where this, or it's unclear why they choose this G, this particular function. And that does a lot of work because they end up essentially differentiating this to get a conformal metric density, which they eventually use to construct the Riemannian metric. If you could choose some other function, or you might ask, why does it have this particular form? Could I choose something else? And what kind of geometry would I arrive at then? And this is what Lamezel and Perlich look at. They essentially say, if I generalize this G, you can construct not a Riemannian metric, but a Finsler metric, which is a generalization of a Riemannian metric. Where I'm by no means an expert in Finsler geometries, but a Finsler metric is constructed by differentiating a function of both coordinates in the base space and the tangent space. So if that's true, then the particular choice of G has kind of implicitly restricted us to Riemannian geometries, but maybe by making a more general choice of G, I wouldn't arrive at Riemannian geometries, I'd arrive at Finsler geometries. So that's one kind of decision point, or something which I think needs to be stressed, something to push down on in the EPS construction. Another point where this kind of thing seems to happen is the second projective axiom. So this says for each event in the manifold, there exists a coordinate system defined in a neighborhood of that event and permitted by the differential structure, such that any particle through this event has a parameter representation x bar, such that d2x bar by du squared is equal to 0. This is essentially kind of getting normal coordinates in. Now, something that's worried me, I would be interested to hear what you all think, is that, well, this condition, the existence of normal coordinates, holds only for symmetric connections. So there's a worry that this kind of axiom excludes torsionful spacetimes by fiat. So insofar as you're interested in any kind of torsionful spacetime theory like teleparallel gravity, Poincare gauge theory, you might be suspicious of this axiom. You might again think that by imposing it, you've implicitly forced us to be dealing with a Riemannian geometry, or to arrive at a Riemannian geometry. The third case to flag is the most famous one, which Martin's already picked up on. So we arrive at Weyl geometries. They then essentially by fiat exclude the second clock effect to arrive at integrable Weyl geometries and eventually at Riemannian geometries. But where does that exclusion come from? It's not at all obvious. And you might think that just ruling it out by fiat kind of runs counter to the grain of the EPS methodology. You're making an empirical statement about the behavior of clocks, so they don't manifest the second clock effect. But right at the start of their paper, they repudiated discussion of clocks. So kind of an open question about what is going on here. Could the exclusion of the second clock effect be motivated in a better way, which is more consistent with their methodology? And that's again something that physicists have thought about, and which I'm just about to mention. So I think it would be really of value to the community. And like I said, this is something that Niels and I are trying to do, just to go through very, very explicitly what's going on in this proof, to make all of the geometrical constructions completely explicit in a way which is going to satisfy us philosophers, and also to point out the places and to assess the places where you might think that they are excluding certain geometries by fiat. Okay, so where have things gone since the 70s? So there have been lots of subsequent modifications to the Ehlers-Pirani shield approach. As yet, there's been no systematic review of these, but I just want to point you to a few of the places or the things which I find the most interesting. So the first is that the Oxford mathematician Woodhouse has sought to extend the APS methodology to the topological structure of the manifold as well. He has a paper from just after the EPS paper, in fact, in Journal of Mathematical Physics, where he tries to do this. Another interesting avenue of pursuit regards the kinds of matter around which you're formulating your constructive axiomatization. So in 91, Ordretz and Lamazal sought an alternative constructive axiomatization, but in the spirit of EPS, which takes as input not classical point particles and light rays, but rather quantum mechanical objects, and tries to build up the structure of the Riemannian manifold from that. Definitely worth pursuing more, and to my knowledge, no philosopher has looked at this area of the literature yet. The third thing kind of comes back to my point about Weyl geometries, which I was mentioning a little earlier. So the apparent reliance on clocks in ruling out the second clock effect has, it seems, been circumvented in papers by Perlich in '87 and Schmidt in 1995, where those authors try to construct clocks or give a construction of clocks in Weyl spacetimes using just light rays and freely falling particles. If this works, then maybe you have a notion of a clock which you could appeal to when you're ruling out the second clock effect, which might go some way to, overcoming the concern about ruling out the second clock effect by fiat, by pointing to any kinds of complex clocks, which seems to be what EPS do. So there's definitely been work to kind of bolster that quite quick move which happens in EPS, and Perlich and Schmidt are people that have tried to do that. There's also a philosophical conceptual critique. So a lot of the interest in EPS came about in the late 70s from philosophers and kind of died down after that. But one of the clearest and nicest philosophical discussions of EPS is from Sklar in a 1977 paper, where he presents quite a, I think, deep criticism of the project. So he writes this: when we move on to the role that particles play in the EPS formalism, we see that any hope of totally undercutting the conventionality thesis about the metric is unsupported by the formalism. The EPS formalism assumes that we know what a free particle is. The idea here is this. We started off assuming that we knew what a free particle is. But if you have a kind of geometrical way of thinking, then you might think that you can only know what a free particle is if you already know what the space-time structure is. It's an object which is following geodesics of whatever particular space-time structure you're thinking of. And so the approach is kind of circular. If you already needed to appeal to space-time structure in order to underwrite the notion of a free particle, then space-time from elementary assumptions, rather you put it in at the start. Now, the right way to go there is probably to come up with some operational procedure to identify or to designate what the free particles are, rather than supposing that the way to cash out what a free particle is with respect to space-time structure. Now, there are a collection of maybe, I don't know, 6 or 7 papers by Coleman and Corte from the 80s where they try to do this. This is yet another place where I think we need more systematic engagement with the literature. Coleman and Corte's papers are very deep and often very, very technical, but they claim to overcome these Sklar concerns. Just to give you a brief sketch, the idea is this: they introduce a monopole criterion, which says if 2 particles, which is what they call monopoles, of the same class are launched at nearly the same event with nearly the same 3 velocity, then under all external physical conditions, their worldline paths will be nearly the same. What does that mean? Well, the thought is roughly that we're going to classify particles by how they behave. And if they follow roughly similar trajectories, then they should be understood as being subject to roughly the same force. And from that, they're eventually, in a way which is, like I said, very technically involved. It uses the machinery of jet bundles and so forth. I'm actually kind of skeptical that it works, but I just need to understand it better. They claim that from this input assumption, or this monopole criterion, they're going to be able to identify what should be regarded in an objective way as the free particles. I really don't see how that could pan out, but that's the claim. If that's right, then they've evaded the Sklar concern. Like I said, I'm skeptical. I guess my current concerns are something like this. So even given the monopole criterion, even given the assumption that particles that follow roughly the same trajectory should be understood as being subject to the same kinds of forces, don't we still have to assume which of these trajectories is going to be regarded as the force-free trajectories? Moreover, suppose that I've got 2 very distant particles. How do I classify whether they're subject to the same forces or not? How do I decide whether they're both free or not? These seem like questions which I would like to understand better, but we all need to, well, those of us who are interested in this project need to engage with Coleman and Corte to see what they're saying about these things. The only person that, to my knowledge, has really engaged with them in anything like a systematic way is Brian Pitts in his 2006 paper. But there's much more to be said with respect to whether the Sklar criticism of EPS goes through or not. A few more foundational remarks, and then I'm looking forward to discussing with all of you. So there are other approaches to constructing the metric field of general relativity from supposedly more empirically acceptable input assumptions. Just to give 2 examples. So something that Tushar Menon and myself and also Oliver Pooley have been interested in for a while is whether one can extend Nick Huggett's regularity relationalism about space-time theories, according to which space-time structure is to be regarded as associated with the symmetry properties of the laws, which can be written down in a way which doesn't make any spatiotemporal assumptions, to the general relativistic context. This is another way, if it works, of extracting the space-time structure of general relativity from just the behavior of matter fields. It would be nice to have a good comparison of the relative virtues of these approaches. Another thing is some interesting work by Hale and Eitin from 2004, where they claim to extract the structure, the signature of the metric, from what they call pre-metric electromagnetism. So they write down a version of electromagnetism written in the language of differential forms with no geometrical input assumptions, but they claim to be able to derive the signature of the metric from those assumptions. So this is another case where you start off with something to do with matter and you derive or extract space-time geometry. Again, it would be useful to think about the relative virtues of the EPS construction versus this. Here's a few obvious things that you could say. So insofar as the latter recovers only the signature, it's clearly less general than the EPS approach. Here's another thing. So Hale and Eitin show that the Lorentzian signature follows only once you make certain extra assumptions in pre-metric electromagnetism. So just as we were worried about the issue of conventionality, conventionally identifying what the force-free particles are in EPS, it looks like something similarly conventional happens in the Hale-Eitin case, where you have to make extra non-empirically motivated assumptions in order to be able to extract something about this geometrical structure of space-time. So it would be interesting to think about the extent to which issues of conventional choices enter these different approaches. There's also a very, very general philosophical point, which is that you can understand constructive axiomatizations in either an epistemological or a metaphysical way. So the epistemological understanding would be this: how do I use certain empirically accessible quantities in order to gain operational access to certain structures which are not directly observable? So in that case, the thought would be, in general relativity, I've got a metric field out there. I have empirical access to the trajectories of freely falling particles and light rays. Can I use those to figure out what the structure of the metric out there in the world is? And if you feel a force of Sklar's concerns, then the thought would be, presumably, you can't fully do this because you have to make certain assumptions, conventional assumptions. And the conventional assumptions you make about which the force-free particles are might lead you to construct a geometry which is not, in fact, the geometry in the real world. But there's also a metaphysical reasoning, which is, can I ontologically reduce certain structures, in this case, the metric field of general relativity, to more directly observable structures? In this case, the thought would be the metric field of GR isn't actually something out there in the world. It's something which is constructed from these empirically accessible structures, the parts of freely falling particles and light rays. And insofar as there's conventionality a la Sklar, you might think that it's, say, metaphysically indeterminate what the space-time geometry of the world is. Usually these discussions have an epistemological rather than metaphysical flavor, but I think that both deserve to be explored and made explicit. Okay, so let me summarize. So constructive axiomatics seeks to build up a theory from empirically acceptable assumptions, axioms. We saw the supposed problems with Reichenbach's original approach. EPS generalized Weyl's work into what's regarded as being the kind of the best, most complete version of a constructive axiomatization of general relativity. But there are open questions regarding both whether what EPS claim follow from their axioms in fact does follow, and also whether they exclude certain geometries by fiat. I've told you about some of the developments of EPS, and I've also said that constructive axiomatizations can be afforded both this epistemological and this metaphysical reading. So clearly much more to do, but I hope that gives you a flavor of what I think is a very, very interesting debate area of the literature for listening.
All right, well, thank you very much, James, for a lovely talk. I suggest that we get questions underway. Is someone's mic not working? Is there a sound issue? Okay. So questions away. I see a raised hand from Tushar.
I think that might be too sharp.
There's a microphone issue. Tushar, I'm just going to mute you to see if it's you, okay? I think it is, because now there's no issue. So why don't we come back to you and you try and fix your sound issue. I see that Peter has a question.
Yeah, so great talk. I really enjoyed it from start to finish. I wanted to go back to this question of the admissibility of clocks and rulers, and wondered, Einstein is in a debate about this already in special relativity when Philip Frank tries to construe him as a positivist, and Einstein says no, and Einstein is perfectly willing to talk about clocks and rulers where you can't have clocks and rulers at scales where you can't have clocks and rulers. But there's been this tension around what the status of such interventions are that go back to positivist, anti-positivist, or quasi-positivist commitments, really that begin not in the period of special relativity and then carry on into Einstein's use of clocks and rulers in general relativity. So what I wondered is, what can you say a little bit more about what precisely, on what grounds are the objection to the complexity of a clock in the discussion over the constructive foundations taking place, for instance, in EPS? Is it a denial of the positivist criterion? Is it a sense that any realistic clock that you could make would interfere with some idealized notion of being able to pull out temporal or spatial measurements without interfering with them? Is it something that gets, when you're in a quantum domain and you can make a clock now that's 5 nanometers or so? Does that address this, or yeah? So I just want to get at the issues that come out of the positivist, anti-positivist axis.
So I'll say something about rods and clocks, and I'll see how much it helps. So suppose that you have idealized rods and clocks, then you might think that you can construct a space-time geometry which codifies the behavior of those rods and clocks, idealized rods and clocks. But there won't still be, it's not like you've solved all of the riddles there, because you haven't, rods and clocks generally are very complicated objects, and you haven't explained why it is that you have these stable rods and clocks to start off with. And as, for example, Brown and Pooley say in their work, to do that, you would need to have a full quantum theory of matter. You would need to know the fundamental constituents of the rods and clocks. And we definitely didn't have that at the start of the 20th century, and arguably we still don't have that, which means that if you want to build up the space-time structure in a way which doesn't assume that we have knowledge, which in fact we don't have, then you might think that rods and clocks are not the right way to go, which is perhaps some of the motivation for instead going to something much more simple, namely the trajectories of particles, and maybe you can build up or reconstruct space-time structure from that rather than from the constituents of rods and clocks. That's something to say about rods and clocks. Could you perhaps, so I didn't think I fully answered your question though, because I'm not exactly sure. Can you say a bit more about what you mean by the positivist criterion?
Well, I think what Einstein was worried about was, Einstein never thought that you actually had to be able to transport a physical clock. He was willing to make a kind of in principle statements about clocks at atomic scales without having any particular or specified idea of what a clock at an electron scale, would be. So, you know, Einstein, as I read him in his renunciation of Franck's trying to assimilate him into a positivist program, was to say, you know, yeah, I mean, Einstein uses positivism, and he says this as a way of stamping out bad ideas, but he's not a dogmatic positivist in the sense that he doesn't actually think you have to be able to specify a clock at an atomic scale to be able to talk about what happens to time at scales. But I think Harvey has something to say, and I think maybe on to point.
Can I come in here?
Yeah, no, absolutely. I was just
thank you. Oh, thank you very much, Peter. I was going to say, in relation to rods and clocks, that, you know, Einstein expressed severe qualms about the role of rods and clocks in his autobiographical notes. But I think it's fair to say that his concern with their role in the foundations of the theory really came about through his discussion with Weyl about the Weyl unified field theory and the role of the second clock effect and so on. That's what really made him start worrying about the fact that, you know, rods and clocks are very complex entities, and there's a whole dynamical story behind them that has to be somehow played out in full. But could I just come back to the role of the sort of more primitive things like freely falling bodies and light rays in EPS? And the point that I wanted to make here was that there are subtleties here. No matter how primitive we think these things are, there are subtleties. You're going to have trouble in relation to the world lines of freely falling bodies if these bodies are rotating. This has been known since the 1950s. But it's not just massive bodies. It depends on how you model, for example, what light is. Now, Eddington, I think, was the first to argue that what light does in general relativity depends on the Einstein-Maxwell equations. And in particular, what happens to the behavior of light in the geometric optics limit. In other words, for Eddington, it was by no means obvious that light would propagate along null geodesics. This is something that had to be shown dynamically. In 2015, it was shown empirically through experiments on extremely delicate experiments on the propagation of photons in vacuo, that depending on the transverse structure of the wave packets representing photons, their group velocities were actually less than c. This was established empirically. I mean, it's a tiny effect. But again, the qualms that I have about EPS is that these kinds of subtleties in relation to the operational definitions of the fundamental entities of special relativity are overlooked. These are very, very idealized assumptions that really don't necessarily strictly correspond to the behavior of arbitrarily chosen freely falling bodies, whether they're massive or massless.
Yeah. So thanks. That's really helpful. So I think in response to what Peter said, I think what a lot of Reichenbachian constructivists would say is that Einstein was making too many empirically ungrounded assumptions, hence the need to use primitive particles, which are apparently more empirically directly accessible, which goes along with the kind of positivist motivations. But I think Harvey's point is absolutely right, that these particles are still, as used in the EPS construction, idealized objects. And we have to be very sensitive to how they actually move in physical practice once they are appropriately modeled. So light rays appropriately modeled using, say, Maxwell's equations in curved space-time. And in fact, if Martin is happy, one of the things that I wanted to speak about next week was whether, in fact, light rays do always propagate along null geodesics. And you can imagine that being a problem in exactly the way that Harvey indicated. It's kind of an input assumption that,
could I just
you might wonder how much EPS breaks down if, in fact, light rays sometimes have different velocities.
Coming back just to Peter's question and his remarks, I forgot to mention that I think a wonderful historical analysis of the anguish and travails that Einstein had in relation to rods and clocks in the foundations of relativity theory has been given by Marco Giovanelli in various papers, particularly in studies in the history philosophy of modern physics.
All right, thank you. I see that Tushar had a hand and so why don't you go ahead?
Hi, are things better now?
Yep, they are.
Okay, brilliant. I disconnected my camera, so sorry you can't see me. But yeah, thanks a lot for the talk, James. I'm obviously wholly on board with this project, but there was one aspect of the motivation that didn't quite make sense. So I just wanted to ask you about that, just for a bit of clarification. So you presented it as a failing that EPS makes assumptions that rule out, for example, non-integrable geometries or Finslerian geometries, that they rule them out by fiat, right? But in a sense, isn't that kind of the point of the project? It sort of seems like the point of the exercise is to recover GR, not different geometries that might be sort of applicable to the world. And so in that sense, isn't, in a sense, what EPS doing the following? They're sort of identifying the physically reasonable, non-trivial assumptions that one would have to make in order to recover GR. And in a sense, it's not going to be surprising that you have to put in non-trivial assumptions to get out something, sufficiently specific.
Yeah, I see what you're saying. I struggle to, for example, take that case of the G in the light axiom 1 that I was talking about. That's not like a physically reasonable assumption that you put in. They just say, we are interested in this function. And the right response there seems to be, why are you interested in that function rather than some other kind of function? And maybe if you have some other kind of function, you have a different geometry. So unless you can motivate the restriction to that particular form of G on empirical grounds, which they don't, I think that all you can say is that what's empirically accessible to us commits you to a broader class of geometries than just Riemannian geometries.
Just a finger on that, Tushar. You don't mean GR, right? You mean some form of Lorentzian manifold on which.
Yes. Yeah.
Yeah. Okay.
Sure, but I mean, in the broadest sense, right? Any Lorentzian metric will be compatible with some stress energy tensor. So in that or some rank 2 tensor that has the appropriate mathematical properties. That's the only sense in which I was talking about recovering GR. If you've got sort of physically reasonable further assumptions on energy conditions and the like, then yeah, absolutely, I agree. But just can I just have just a small finger on just on James's response?
Mm-hmm. Of course, yeah.
So it seems like what EPS are. So from my memory of this, and this is really more from the Jürgen Ehler 73 paper than from EPS. But my memory of that is that they're not trying to. It doesn't seem like the project is to try to think of all and only the physically reasonable assumptions and then see where you get from there, but rather to sort of accumulate a set of physically reasonable sufficient conditions to allow us to deduce sort of various facts about metrics. And so in that sense, I don't know, am I just kind of, are we just reading the project differently?
But how is this assumption about G a physically reasonable condition?
Oh, so physically, I guess I'm thinking about this maybe backwards. So so it seems like you're saying something like, why restrict to this when the world could be such that it could be some other, there could be some other restriction. And what I'm saying is that's perfectly consistent with thinking, well, yes, but maybe those, maybe some of those others would not lead to GR. And of course, it would be a non-trivial thing to demonstrate that, and they haven't done that. But it sort of seems like it's still it's part of a larger project to understand sort of the broad conditions under which it would be possible to recover a metric, and then see if those assumptions kind of are consonant with what we would think of as being physically reasonable, rather than starting off with things that we think of as being physically reasonable and then seeing where.
So you start off with certain what they claim to be empirically well motivated axioms, and you get a certain kind of class of geometries which might be richer than Riemannian geometries, and then they say, well, if I had such and such extra conditions, I would restrict to the subclass of Riemannian.
Yeah.
in that broader class. And then it's a follow-on project whether those assumptions can be motivated in any particular way.
Yeah, absolutely. Yeah, yeah.
Okay, I see that Jacob has a hand.
I've accumulated a couple of questions.
Can you
First off,
be a bit louder? We can't hear you.
oh, I'm sorry. Can you hear me now?
Yeah.
Okay. First question. So Harvey, you mentioned a 2015 paper about group philosophy of light. I'm just wondering if you can let me know what that paper is.
Yes, I can. Let me just dig it up for you.
All right. So while you're working,
If you send it to me, I can send it to everyone on the group chat, or I can, I can do something like that, or we'll send it in an email later. We could.
I can certainly send an email. I mean, I've got it in front of me. It was in Science. In fact, do I have it in front of me? Yes, I do. 1 second. It was published in Science in 2015. Yeah, I mean, it's an empirical demonstration that there's a tiny deviation from, of course, it's a bit slower than the light speed c, but photons can be made to travel with their group velocity slightly less than c. And it depends on how you configure the transverse dimensions of the wave packet. And this has been known for a long time, but it was thought, I mean, this possibilities has been known for a long time, but it was thought it was too small to measure, but they have measured it now. So in other words, you don't really need to go to the exotica of, extreme geometrical conditions and Kerr solutions, for example, to see that, that the null geodesics are not necessarily identified with the behavior of photons in vacuo.
if you just have the authors' names, though, that would be really great.
Yes, Daniele Giovannini. There's actually several authors. Jacqueline Romero, Vaclav Prodacek, Gergely Ferenzi, Fiona Spirits, Stephen Barnett, Danielle Faccio, and Miles Padgett. But I'll send. I can send the details.
Thanks. I had a quick, maybe technical question for James. James, if you could go back to the slide on the monopole criterion.
Oh yeah.
By the way, I didn't say this, but this was a fantastic talk. It was amazing. I just wanted to make sure I said that too. So I'm a little confused about this. Doesn't this presume? So I take it that the point here is that we're going to put particles into equivalence classes, saying that they, have the same force acting on them.
Yep.
Based on this idea that if they begin with nearly the same initial conditions, then their future world line paths will be nearly the same.
Yep.
Doesn't this presume that gravity is going to be non-chaotic? And don't we have counterexamples? I mean, in de Sitter space-time, don't paths diverge exponentially if they have slightly different initial conditions?
Yeah. I mean, that seems like a pretty good point to me. So maybe you wouldn't, yeah, I mean, I can definitely see where you're coming from then. So the monopole criterion just wouldn't seem to be a good guide to whether particles are subject to the same kinds of forces or not.
I mean, we live in a universe that's obviously not exactly de Sitter, although they've had a de Sitter phase, but we live in a universe that's becoming more de Sitter with every passing moment. Yeah.
I mean, I definitely feel the force of your concern there. I don't want to say anything too quickly because, like I said, their paper is unrelentingly technical, and I could feel like I understand about 15% of it. But yeah, I mean, at the moment, I think I share your concern. Actually, I hadn't thought about that, but maybe I can say a bit. So just, I don't know how much I said about this in the talk. So after they've put down the monopole criterion, Coleman and Corte say we're going to show from just differential topological assumptions how one can identify one monopole class as being the force-free particles. I just don't see how that can work, but then I don't understand the maths that follows, so more needs to be done here.
Thanks. So also the Aldrich-Lammergall paper.
Yeah.
What do they mean by quantum waves? I haven't seen this paper before, but you said they wanted to replace the use of particle trajectories with something more like wave functions in quantum mechanics.
Yeah,
do you know what they meant by waves?
I think they mean certain kinds of solutions of the Schrödinger equation. But yeah, I'm not exactly sure. I can that is easily checkable. I can have a look at the paper and tell you, but I'd need to say something precise.
So another quick question. Maybe I'm missing something here, but this constructive approach, right? This idea that we take certain empirical facts and attempt to build up, the metric or the manifold of spacetime or something like that. How does the Einstein field equation emerge from this? How do we get? I mean, the idea is to rebuild all of GR.
So I've thought about this question as well. I think they don't say much. They just, once they've constructed the metric, the thought seems to be that they're done. But there is a legitimate question about, what happened to the stress energy tensor? And I think it must have some, although they don't say it, I can't see it working in any other way other than the way that Tushar indicated earlier, which is just to say, once you've got a metric, I will just backwards define a stress energy tensor using the Einstein field equations.
But hang on a second. The idea is to rebuild the entire theory.
Mm-hmm.
You can only rebuild the stress energy tensor if you posit the Einstein field equation, right? I mean, what it seems like they're establishing here is that there's a correspondence between empirical structures involving light rays or particles and the kinematical structure of GR, the shape of the space-time manifold metric. Yeah. But that's only part of the theory. Then there's this whole other part that says that there's a relationship between that structure and the stress energy tensor. And sure, if you posit the Einstein field equation, you can reconstruct the stress energy tensor. But where does the Einstein field equation come from in this? And why uniquely the Einstein field equation? I mean, after all, there are other. I mean, there are other field equations you could write down, and this doesn't seem to fix that at all. Yeah. So how is this claimed to be a constructive approach to all of GR in that sense?
Yeah, it seems like it would be more acceptable to say it's a constructive approach to the kinematical structure of general relativity.
That was my finger on Tushar's point a while ago. That was exactly what I was saying.
Yeah.
And I had one last, hopefully very quick question. Way at the beginning, you talked about the constructive approach versus the deductive approach. If you'd be kind enough to go back to the beginning, I'd appreciate that. And this is my last point. I'm sorry to.
Where is it earlier than this? Wait, sorry, did I miss it? There you go.
Deductive axiomatization. Okay, so step 3, correlate various objects to deduce theory of the empirical world. What does that mean? Does it mean that you start with an entirely mathematical framework and you look for patterns in it, and then you compare those patterns with things that you see empirically in the world? Is that the idea?
Yeah, exactly. Exactly. So you start off with some really basic assumption. It might be like logic or set theory or whatever you please. You end up building up your theory, and then you say, now I've got my theory. These light cones can be associated with the parts of massless particles, but you do that at the end rather than at the beginning.
This worries me. If you're not going to put any, I mean, of course, this is not the approach you're taking, but I'm very confused about this approach, because this is in a totally different context. This is basically the Everettian approach to interpreting quantum theory. You start with a totally mathematical set of statements, and then you look for patterns in the resulting theory that you can correlate or identify with things that we see in macroscopic reality. But the problem with these approaches is if you're starting with a completely mathematical story with no empirical connection put in at the outset among the axioms, well, mathematical structures are highly malleable. You can transform them. You can produce all kinds of patterns. How do you know which patterns you need to reify? You can only state which patterns have to be reified by having as one of your assumptions that certain patterns are to be regarded as ontological and others not. I don't see how a deductive approach could possibly work. This, of course, only favors taking the constructive approach, but I'm deeply confused about deductive approaches in general. I don't know if you had a comment to say about that. That maybe this is off topic, but
I hadn't drawn that connection before, but in a way that worries me, because I haven't ever much liked Bohmian mechanics, but I also like constructive approaches. It seems like the primitive ontology approach is more in line with the constructive approach.
right. I was going to say primitive ontology approaches seem to be much more in line with, yeah. Okay, that was all my comments. Thank you. And thanks again for a wonderful talk.
Thank
All
you.
right, let's go to Carl. I see he has a hand up.
Yeah, enjoyed the talk very much. When you were putting up one of the last slides, you were talking about epistemological versus metaphysical approach, and just the metaphysical, the way you characterize the metaphysical project maybe immediately raised a doubt in my mind, because just because you can reduce doesn't mean that it's the right thing. And I was thinking about it in connection with gravity waves. I mean, if you give a reductive story about, as it were, how you construct the metric out of the behavior of things, does that show that it's not real? And the general way that people think about gravity waves is indeed that they're real. In fact, we wouldn't know how to explain how certain photons and other bodies wiggle otherwise inexplicably without postulating giving them some sort of reality. But then, so I'd like you to say something about that if you can, but also, is the EPS project actually able to, from its sort of empirical starting point, give us the complete metric for any GR spacetime full of however much kind of weird gravity waves of various strengths you want?
I think the answer to the second question would be yes, in light of the Weyl result, right? That any metric can be uniquely specified by projective and conformal structure. And so take those pieces of projective and conformal structure, you could reconstruct that metric.
You have to have enough bodies. You have to have sort of space-filling test bodies to... Yeah, okay.
The first question, yeah, so if this is right, if you're following the metaphysical story, then you wouldn't say that gravitational, ultimately, any account that you give of gravitational waves influencing the motions of photons, say, would be a roundabout story in terms of just the behavior of photons and massive particles. It would be a convenient shorthand.
Okay, thanks.
Neil? Neil Dewar?
Hey, sorry. So this question's actually on behalf of Josh Eisenthal,
Okay.
who is on a train with a very dodgy internet connection. So send this to me via email. But
You've just muted yourself.
yeah, that was an accident. So Josh says that, so following up from Tushar's question, that he's also wondering about this criticism that EPS is going to rule out Finsler geometries by fiat, and the thought that this might be something that a constructive axiomatization is supposed to do. So Reichenbach begins the axiomatic by saying that the value of an axiomatic exposition consists in summarizing the content of a scientific theory in a small number of statements, so that any evaluation of the theory may then be limited to an evaluation of the axioms, because every statement of the theory is implicitly contained in those axioms. So if we are trying to axiomatize GR in this sense, then one or more of the axioms should indeed rule out general Finsler geometries, precisely because GR doesn't employ such a geometry. So in other words, we discover that we should, if we discover that we should in fact employ a general Finsler geometry, then we would be revising or abandoning GR. So the constructive axiomatization is helps us to see what empirical assumptions the theory actually makes, and hence where we might revise the theory in the future. Mm-hmm. Yeah, I'm also interested in this question.
Speaks to the stuff that Tushar was saying about you can see things in either direction. It might be that your end goal is general relativity and you write down your axioms such that you get general relativity. And then, as we did when we looked at the first light axiom, you can say, well, maybe I can relax or generalize this axiom. Fair enough. The other way to go would be to say, I only want empirically well-grounded axioms, and then I would arrive at a richer class of geometries, and then I can think about what extra things I would want to impose such that I restrict to general relativity. I think ultimately these things arrive at the same place. They're just different ways of looking at it. I don't find anything too objectionable in what Josh said there.
All right, Richard, and then we'll go back to Tushar, who has a finger and a question.
Hi, interesting talk. And I wanted to go back to the point of having the transfer structure of light rays, making it such that the group speed is slower than the speed of light. I want to compare that effect to the effect of the index of refraction of just not having a perfect vacuum in any realizable astrophysical scenario. There's obviously there's matter in all parts of space, and even if there isn't at one moment, there's an uncertainty principle that's going to make vacuum polarization create matter. And if this effect of the index of refraction is slowing down the light even more than the typical deviations in some of the transverse E and B profiles of these photons, then would the best that we might have in order to construct a light cone structure to help validate GR be just have expectations for how the light cone structure would vary from one index of refraction to another, and then compare that with data, and then make some sort of hopefully analytic continuation to what the light cone structure would be if we didn't have this effect. So yeah, I guess like I'm just wondering in practice, what can we do as a workaround given we have the ability to make measurements in the astrophysical world that we have, but there are these effects.
So I've got a few other things to say, and I guess maybe Harvey does as well. So another interesting paper, which maybe I'll talk about next time, is a 2017 paper by Arsenio and Hodgman, where they think about the propagation of light rays in curved space-time. And they show that in general, again, you won't get, or they claim to show that in general, again, you won't get invariably null propagation because the space-time curvature, they say, is changing the refractive, can be understood as changing the refractive index of space-time. So there's an interesting set of claims about whether light always propagates on null geodesics or not. That's the first thing to say. The second thing to say is, your question was, well, how do we then, or at least I understood you were saying, how do we then figure out what the light cone structure or the causal structure is? But there are other ways to do this. So just one thing to flag is that the group velocity, which is what most of these people look at, isn't necessarily best identified with the signal velocity or the front velocity. And there are various proofs, for example, by the Cambridge mathematician Friedlander, that the signal velocity is always c. And so even if you're getting changes to the group velocity, you might think that the light cone structure is given by c is still special in some way.
I'll have to look into that.
Could I just a finger there? The 2015 paper refers to an experimental demonstration in, I think it's 1992 for the first time, that light inside glass, photons inside glass propagate at the group velocity, not the signal velocity.
Really?
So yeah, so they're using this result to bolster their own claim. Now, I'm not an expert on this, and I can't vouch for the 1992 result, but that's what they're claiming.
Thanks. Tushar, I think you had a finger and a question.
Yeah, thanks, Martin. The finger got resolved, so this is a change in direction question. But James, right at the end, you had a slide where you discussed construing this as a metaphysical or as an epistemological project.
Yeah.
I just wanted, I mean, this is a slightly nebulous question, but I just wanted to get your thoughts on a third option, which would be to construe this as a semantic project. So it seems like if you construe this as a metaphysical project, you're kind of going to be led to relationalism, so sort of austere relationalism, and then run up against the precise sorts of worries that Carl articulated about gravitational waves, about which, as you know, we have various sort of fancy footwork stories that we might like to tell. But in light of this being sort of this tracing its way back to people like Reichenbach, is there a way of reading this as just saying, well, let's put on hold any sort of further axioms about how you might relate the semantics to the metaphysics and, you know, be positivists or whatever. And just construe this as a way of understanding what it is that we refer to when we refer to, you know, a metric of general relativity.
Yeah, I think so. I think that is a legitimate third option. The thing that just came to my mind, I don't know if the connection breaks down, is, do you think that this is similar to, maybe not, similar to Knox's spacetime functionalism? Like,
How so?
Well, what we mean by spacetime is what picks out a structure of inertial frames. You could say something similar here of what I mean by spacetime is whatever is associated, whatever can, I don't know how to put it, whatever.
Yeah. Yeah, I mean, that makes yeah, I mean, it makes complete sense for that to be the case, because if you, as Butterfield and, well, Gomes and Butterfield do, if you read Eleanor's functionalism as a special case of the Lewisian project, that Lewisian project is pretty explicitly semantic. So yeah, I think.
Yeah. So yeah, I fully agree though that there does seem to be this third option here. Thanks.
All right, great, thanks.
All right. Do we have any more questions? Okay, I'd like to ask you. I mean, I'd like to. I mean, I've wanted to say this from the beginning, but I decided to let everyone speak before. Thank you, James, for a beautiful talk. I think it was really flowing and well explained. Maybe I would have liked for you to go a bit slower at sometimes, but that's just my my ignorance. So what I mean, okay. So the main thing I want to say is the modern mathematical approach, right, towards general relativity has identified a number of questions they think of as interesting and relevant, etc. Strong cosmic censorship, etc. And the championing viewpoint is, of course, PDE. So field equations, field equations, field equations.
Yeah.
And if I look at your slides and I think, okay, well, you know, one thing that the field equations have revealed, and this would have been totally opaque to EPS, because of course this was a different time, was that because PDEs now are the central object of study, regularity is going to be the central object of study.
Mm-hmm.
And in particular, whether or not some, you know, some might say not fundamental, others might say some truly fundamental, but some of those aspects of general relativity, like strong cosmic censorship, hinge ever so sensitively on regularity. So from the mathematician's perspective, the way it goes is more like this. It's like, fix a G that's in some regularity class, and then try to make of the initial value problem what you will, and try and go as far as you can with that. So you may start with some initial data prescribed on null hypersurfaces, on a space-like hypersurface, etc., etc. Now, I was looking through EPS as your talk was going on, and in the question, and I could see that you know, at the time of writing, they obviously didn't have any feeling that that the world would turn out this way, and of course regularity all over the paper is assumed. And in particular, I came to notice that actually some of the very axioms that they have are strictly false, right?
Really? Okay, cool.
Yeah, strictly false. So you know, for modern treatments of regularity, the things like the Weyl property of the light cones and stuff like that, that just does not hold. Something like bubbling happens, which is a kind of phenomenon associated with non-Lipschitz functions for your metric in your charts. However, I think that there's a lot of foundational work which no one's done, because I don't think it's been done, to kind of understand regularity better and understand the meaning of what's going on when people try and propose certain regularity classes of interest for various questions of interest. So I guess my question is, what are your thoughts? How do you feel about this? Would you feel it's more of a deductive approach to say, listen, what I'm interested in is the field equations, forget the stress energy tensor for now, just think of vacuum, I want to understand vacuum GR, say, okay, these are my field equations, and then just try and say, okay, for what kinds of metrics and what kinds of initial data problems can I make sense out of this? Or would you be of the inclination to say, you know what, initial data and PDEs, I don't care. I don't care. I think it's not my thing. I don't care. I don't care about what it does and why it's relevant. So I'd like to hear your thoughts on these points.
Mm-hmm. So when you say that the axioms are strictly false, that
doesn't hold. Weyl property of this thing where the geodesics or the time-like geodesics hug the interior of the null cone and stuff, that doesn't hold.
It doesn't hold in general, right? But it might hold in some GR solutions.
Oh, definitely, yeah.
Yeah, so I would take it, I see. Maybe that is, what I was going to say is, they all claim that their axioms are empirically well-grounded, and if they thereby recover only a subsector of GR, they might not regard it as being problematic. They would say, like, this is the empirically salient subsector of GR.
But let me give you, yeah.
Sorry, no, go ahead.
No, okay, so let me give you an example. So suppose I'm interested in fluids, right? Suppose I come up with an axiom system that straight away gets rid of shock waves.
Yeah.
What do we do now?
Yeah, I take the point then. So maybe in like all the knowledge that we've accrued in the last 50 years, the axioms are just, in fact, not empirically well grounded. They rule out certain empirical phenomena that we would very much like to model. Doesn't mean that the spirit of EPS is dead, but you would need to proceed from better assumptions, better axioms.
Well, I actually think it's a very hard question to understand EPS in the sense of regularity. I mean, like just, you know, skimming through the proofs as you were talking and in the question time, I don't see how EPS stands much of a chance without significant, you know, without a significant amount of rejigging. So, I mean, I just want to put forward the idea that from the mathematician's perspective, it feels like it feels like the field equations are really the central object of study. Never mind how you get there. You motivate them with, you know, various things and empirical verification to some degree and stuff. But yeah, the right axiom system for general relativity in the mathematical community is very much an open thing that people don't yet understand, and you know, people don't really understand what's the right kind of object that should feature in these field equations. Are they solutions? Are they weak solutions? Are they, what form do they take? And so this kind of free-falling idea of EPS is I would think would seem very outdated to the mathematicians currently working in general relativity.
Yeah, but I don't know. I mean, you're the expert. I don't know if there are any. Do you think, is there anything obvious as to how one could replace the axioms with something more appropriate based upon our contemporary understanding of general relativity, or is it entirely non-obvious how one would proceed?
Well, I think some people have actually thought about this. So recently I was in Florence, and I met with a guy called Ettore Minguzzi, who is kind of the world champion Lorentzian geometer. So he's kind of developed C0 causal theory from the ground up. He's very interested in Lorentz Finsler type scenarios, and I think that he would have a lot to say on your question. So yeah, that's maybe something that we should email him about, and he's a very nice guy. I'd be happy to, maybe we should get him to talk, and then you can be in the audience and chat to him, etc.
That'll be cool. Yeah, but thanks. That's a super good point and well taken.
Well, thank you for a beautiful talk.
Cheers.
Are there any other questions? Tushar has
I think Johannes had a finger earlier.
Johannes, do you have a finger still? Or?
And I think I wanted to go back to Harvey's point briefly on group velocities and Richard's reaction to that, because I think the significance of this paper is really that it was in free space, because we know that in materials, you can do all sorts of different things with group velocities. You can, if you add some particular electric polarization to the material, you can even have group velocities that are beyond the speed of light, that are faster than the speed of light c. So I wanted to point this out, that the identification between signal velocity and group velocity is very rough, mostly in materials. So I think the point is really that this experiment was done in free space.
You mean you mean in vacuum?
Yes, yeah.
But what, I mean, is that possible? There's a magnetic field around the Earth, right?
What do you mean?
Was it like shielded somehow? Like they created a perfect vacuum where there are no field lines inside this thing, or?
So I don't know about this 2015 paper, I haven't read it, but I know that you can construct materials where the group velocity exceeds the speed of light. Okay. So I don't know, that's why I was cautious of the claim that the group velocity can be different in materials, because we know from before that that's not surprising. But I think in free space, where the group velocity equals the phase velocity, it's more interesting to have deviations from the speed of light of the group velocity.
All right. I believe there was a finger or a hand raised by Tushar at some point. Has that disappeared now? Or?
Yeah, it's gone. Sorry, Martin, I just forgot to unraise it. I got to ask my question. Thanks.
James, your talk finished relatively early, but it clearly generated such a great discussion, because this is one of the longest times we've run this seminar. So thank you. And that's not me saying that I'm closing the seminar now. Please, if anybody has anything to add or ask, please do. Maybe I'd like just to ask a practical question. So you and Niels are working on this project?
Yeah, well, we've been interested in it for almost, just on and off interested in it for 2 years now. So just, I hope that we can at least get some review paper out where we can clearly summarize what is going on in the EPS construction, but also talk about, in a systematic way, how people have revised the approach thereafter, and talk about some of the philosophical problems, including the stuff that's come up today. I guess that would be our end game with this.
That would be great. All right. Well, nobody seems to be asking any more questions. So last chance, 30 seconds, and then I'm going to end the seminar. It's recorded, by the way. So yeah, so that will be available on YouTube as well. It'll be on the BHI website, and the BHI have decided to put the videos on YouTube. So, yeah. But anyway, any last questions? All right then. Well, James, thank you. Thank you so much, and see you next week, everyone.
Yeah, thanks,
and
everyone.
James. All right. Bye-bye, everyone.